So let's talk a little bit about Newton's second law. And before we get to Newton's second law, we got to go back and we got to just review what Newton's first law. So Newton's first, or the law of inertia. And so his first law says that, if there's no acceleration of an object, so if the object is just sitting still or moving at a constant velocity, so constant velocity, keeping in mind that that does include a velocity of 0, then the net force on the object is 0. So we can pull this out and we can analyze it. So his first law mathematically would say that the acceleration of an object is 0 if and only if the net force is 0. Those are vectors. Okay, so let's pull this out and we can see what's going on. So there's my object, and then we can draw our forces in there. So in this case, if it's a ball like on the floor, we would have our normal force and our force of gravity. Keeping in mind that the force of gravity is always mass times g, and we also call that the weight, which is different from the mass. And so what we can see here, because we're at a constant velocity, then the acceleration is 0. And so when we analyze things like that, that's what we would start with. We would say, well, all of the forces are acting in the y direction, so the net force in the y direction is equal to 0. So the normal minus the force of gravity is equal to 0. It's minus because it's pointed down. So we have that the normal is equal to the force of gravity. So that's Newton's first law. And in the last video, I showed you how to analyze these like in 2 dimensions. But now Newton said, well, okay, so we know that if there's no acceleration, the net force is 0, but what happens when there is a net force? So that leads us to a second law. So the second law deals with the net force. So Newton's second. And what it says is that, if there is a net force acting on an object, then we'll have some acceleration. So it's kind of this thing, but we're not changing it. So if the net force is not equal to 0, then the acceleration is not equal to 0. And then we can expand this and do some investigations and see exactly what's going to happen. So let's suppose we had a like a block or something on a frictionless surface, and we just apply a force to it. So again, no friction. So what we have here is we have an imbalance in the x direction. Let me draw a force diagram so that we can see what's going on. So we have this block, and then just like in the previous case, we're going to have a normal force and the force of gravity. But now we added an additional force in the x direction. So while I still have equilibrium, that's what this is called. That's equilibrium. So balanced forces. So although I have equilibrium in the y direction, I now have an unbalanced force in the x direction. And so this is going to produce acceleration. This unbalanced force will cause acceleration in the box. And so if we did some investigations, what we would find, if I plot acceleration versus the force, and this is just the force applied in this case, but in general, this would just be your net force. As I start increasing this force, I would get more acceleration. So, for a certain amount of force here, I would get some acceleration. And then if I double that force, I'm actually going to get double the acceleration. And so on. And so if I did this experimentally, this is what I would find, that the acceleration is increasing at the same rate as the net force when I hold everything else constant. And so this is a linear relationship. And so what we can deduce from this is that the acceleration is proportional to the net force. So then we can also say, well, is there anything else? So if we were investigating this, we would look for any other things that might affect this, because we know the net force will cause an acceleration. That's clear. And then now, once we experiment on it, we can see that the acceleration is proportional to the net force. Well, what happens if we keep the force the same, but then start changing the mass? Well, if we do that, if we do that, then what we end up with is a graph that kind of looks like this. So the acceleration, as I increase the mass, what's going to happen is it's going to drop down because it's going to get heavier. And again, I'm applying the same amount of force. And then it kind of lays down like this. So we would get this kind of graph. You should recognize this. This looks like a rational function, and that's what it is. And so what we see is that the acceleration is proportional to 1 over the mass, or it's inversely proportional to mass. So as the mass goes up, the acceleration goes down. As mass goes up, acceleration goes down. And that's the opposite of force. As force goes up, acceleration goes up. And through experimentation, we can show that there's nothing else that affects it. So it's only dependent upon the net force and the mass, and that's what leads us to the mathematical statement of Newton's second law, which is that the acceleration is equal to the net force divided by the mass. So this is Newton's second. And we can rearrange it. If we multiply mass over, we get the net force equals mass times acceleration, and this is probably what you think of when you think of Newton's second law. But I want to point out that this is net force, not force. It's not force is equal to mass times acceleration. It's net force is equal to the mass times the acceleration. This right here, though, I think is conceptually better because it says that the acceleration is dependent upon these two, which is true. You have to have the net force first. This is the cause, this is the effect. If you change the mass, this is the effect. We'll have a different acceleration over there. So in essence, that's Newton's second law. If we have an unbalanced force, we're going to have an acceleration. Now, applying this, one other thing. So keep in mind that it's through the acceleration we can also think about the change in velocity over time. So if I double the force over the same amount of time, then I would get twice the change in velocity and such forth. So you can think proportionally all the way over to this, because that is acceleration. Okay, so how are we going to apply this? And a lot of problems will actually be using both of these, Newton's first and second law. So let me do an example so that you can see how this might apply. So suppose, let's go back to the block. Let's change it to green here. Okay, so we have a block on a solid surface, and we're pulling it with a rope at some angle, say 20 degrees. So we're pulling it with some tension, no friction. No friction. So now we can pull out the force diagram, and then we'll think about what's happening in all of the directions and maybe come back and solve something. I don't know if I'll go all the way through the solution. So we have this this block here, and then we can draw the forces on it. So we're on Earth, so we have the force of gravity, which is going to be mg. You also have the normal force acting up. The normal force, although I'm drawing it from the center, it actually acts on the bottom. But I'm drawing it there just so that we can see the balance. And then you're going to have some tension coming off of it. Again, I'm going to draw it like that. So that's my tension. And we have it at 20 degrees. So these are the forces. So what I can see is that there is an imbalance in the force. So I know that there's going to be some acceleration. Then our job will be to figure that out. And what we're going to do is we're just going to break everything, like we did in projectile motion, into our x and y plane. So we're going to look in the x direction, and we're going to look in the y direction and try to figure out what's going on. So looking in the y direction first, I know that this block is not moving up and down. It's not accelerating. So it's got a constant velocity of 0 in the y direction. So in the y direction, you know what, let me move this over. So in the y direction, the acceleration is 0. There's no acceleration in the y direction. Therefore, the net force in the y direction is equal to 0. So let's work with that. So this is Newton's first law. So the net force in the y direction is 0. So let's see, we have the normal force. And then we have the force of gravity down, so minus the force of gravity. But there's another one, and it's on this tension, because we have to break this into its components. So we're going to have a tension in the x direction like this, and a tension in the y direction. So we would get plus the tension in the y direction. That's equal to 0. And then we can put Ty in terms of the tension through trig. So we get the normal minus the force of gravity plus tension, and it's opposite the angle, so that's T sine theta is equal to 0. So if I wanted to know the tension, well, I would have to figure out, the force of gravity would be mg, but I don't know the normal force. But I'm probably not going to finish this. I just want to show you the setup. So now let's go to the x direction. So in the x direction, we have a net force acting in the x direction, so we're going to have some acceleration. So the net force in the x direction would be the mass times the acceleration in the x direction. Notice that I indicate that I'm only working in the x. So the only force acting in the x direction is this tension in the x. So I get Tx is going to be mass times the acceleration in the x, and Tx in terms of t would be t cosine theta is equal to mass times the acceleration. So depending on what I was solving for at this point, you know, maybe tension, or maybe I want to eliminate tension and solve for the normal force. Doesn't matter. So at this point you would just go, you know, back and forth between these with whatever you have and whatever you need. But this is a typical type of problem and how we set it up. So you can see we use Newton's first law and his second law, but in different directions. Okay, the one other example I wanted to do was like an inclined plane problem. So suppose we have a block sitting on an inclined plane. I don't know, 10 degrees, whatever. And there's no friction on this thing. So it's like an ice, a big block of ice sitting on a ramp. So we know that if you were holding it and you release it, this thing is going to go this way. It's going to accelerate in that direction. It's going to slide down, and you know, maybe we want to find the velocity at the bottom or something. I don't know. Anyway, the way that we do these inclined plane problems is it's almost always the same. We might have some forces acting up, but in this case I'm going to keep it nice and simple. What we're going to do is we're going to draw the force diagram right on the inclined plane. Now before we do that, you need to understand what we're doing is instead of doing an xy like this, we're going to tilt this whole thing so that we get this, because we want to make x go down the ramp. So that way x is this way and y is perpendicular to it. So that makes our forces a little easier to analyze. So we're not going to do our traditional one. We tilt the whole thing. So now we can start drawing in our forces. So you have the normal force, which is coming up like so. So that's your normal. But you can see the normal now is in my y direction. And then we have gravity, and gravity is straight down. So that's the force of gravity. But gravity is not in x or y, so this one we're going to have to deal with. We're going to have to get the components of it. So to get the components, what we're going to do is we're going to draw one coming in the y direction. So it's in the y direction, so that's the force of gravity in the y. And then we have a force of gravity in the x direction. Fg in the x direction. So you see there's my yx right here on the forces. And then the angle of the incline goes right up here on the top, 10 degrees. And that's how we'll start to analyze these things. So now based on this, I know that in the y direction, which is kind of at an angle here, this way, the net force is 0. So the net force in the y direction equals 0. And my net forces in the y is the normal and the force of gravity. I'm calling this way negative. So the normal minus the force of gravity in the y equals 0. The force of gravity in the y, though, is the force of gravity cosine theta. That's equal to 0. So we get the normal is equal to Fg cosine theta. So notice what happened though, so cosine theta is going to be a number between negative 1 and 1. So it's going to reduce this force of gravity. Yet when it was on a level plane, what we got is the normal was equal to the force of gravity. And it makes sense, as we start tilting it up, it's less and less force that's pushing back, because some of the force is pulling it this direction. That's my Fg. And if we go all the way vertical, the whole thing would fall because the normal force goes to 0. So that's one of the things we can see by going through this type of problem and analyzing it. Now the net force in the x direction, it's only this. So we're going to have acceleration. So we have Newton's second law. Mass times the acceleration in the x. And the only one is going to be the Fg in the x direction. So that's the mass times the acceleration in the x. And that's going to be Fg sine theta is equal to the mass times the acceleration in the x. I'm going to go ahead and carry this out, because if you're doing this algebraically like I am, then things will simplify, because the force of gravity is mg. So we get mg sine theta is equal to m times the acceleration in the x, and so m is gone. So we get the acceleration in the x direction is just going to be a piece of g. And in the absence of friction, mass doesn't matter, it cancels out. Now if we had friction, that changes. But you can see in a frictionless surface, it doesn't matter. All masses will accelerate exactly the same at g sine theta. So that's one of the interesting consequences that you can pull out by doing things algebraically and seeing some relationships. So I hope that kind of gives you a basic understanding of Newton's second law. You really have to walk through all sorts of different situations and start working through it. But I want you to really pay attention as you're working through it, these types of relationships that pop out. It'll just help you better understand Newton's second law overall.